Welcome to BTEC Revision. In today's lesson, we're looking at conservation of energy. By the end, we should be able to calculate values using the conservation of energy. What is the conservation of energy? It is a physics principle that states that energy cannot be created or destroyed. It can only be transferred. Looking at an example here, we have a ball with a mass of 1 kilogram at a height above the ground, 10 meters. So thinking about the energies involved here, we have the height, we have the mass. So the equation, gravitational potential energy equals mgh, should be coming to mind. The energy here we can calculate. We know the mass is 1, gravity is 9.8, and the height is 10. So this gives us a value of 98 joules. So this means that this ball has the potential energy due to gravity, 98 joules. So if this ball was to drop, this energy will be transferred into kinetic energy. So as the ball is dropping, the gravitational potential energy will be decreasing. The reason why is because the height is going to be decreasing. But this energy must go somewhere. It cannot just disappear. And since it's going to be moving, we can say that this energy will be transferred into kinetic energy, which also, at the end, must equal 98 joules. So this would mean that all of the gravitational potential energy has been transferred into kinetic energy. And when it hits the ground, this kinetic energy will be zero because the energy transferred would turn into thermal energy. And we can write the thermal energy will be equal to 98 joules. So this is the conservation of energy principle, stating that energy can only be transferred from one form into another form. It can never be created or destroyed. Okay, let's look at an example here. Calculate the velocity of the ball as it hits the ground. So from the previous example, we worked out the gravitational potential energy, which is equal to mgh. That's 1 times 9.8 times 10. So that's 98 joules. Now, this energy is going to be transferred just before it hits the ground. All of it is going to be transferred into kinetic energy. And we know the kinetic energy formula is half mv squared. So we need to rearrange this for v. We know the kinetic energy is going to be 98 as well. So we can set these two to be equal. So writing this at the side here, we can write 98 joules of energy is equal to half times the mass, which is 1, times velocity squared. Okay, rearranging this. So 2 times 98 is equal to v squared. So v equals square root 2 times 98. And this gives us a value of 14 meters per second. Let's look at a second example. A yellow ball is rolling along the ground with a kinetic energy of 500 joules. Calculate the velocity of the ball at a distance of 5 meters, including frictional forces. The coefficient of kinetic friction is 0.4. Okay, so we can start by writing down what we have. We have 500 joules of energy in the form of kinetic energy. And we know that this is equal to half mv squared. Okay, we also know that since the ball is moving a distance and there's friction forces involved, this energy must be transferred into thermal energy. So therefore work is done. The work done is energy transfer. So the work done equals force times the distance moved Okay, we know the distance moved is 5. So S equals 5. And the work done is going to be dependent upon the frictional force. So we can work out what the frictional force is if we remember the kinetic friction is equal to the coefficient friction times the reaction force. So we can work this out. We know the coefficient of friction is 0.4, and we will need to work out the normal force. And we know that the mass is 1 kilogram, so we can work out the weight, W equals mg. So that's 1 times 9.8, which is equal to 9.8. Okay, therefore, the reaction force is going to be also equal to 9.8. So the reaction force is 9.8, so times by 9.8 to give us a frictional force, 0.4 times 9.8, which is equal to 3.92 newtons. Okay, so now we have our frictional force. We can plug that into our work done equation. So work done equals frictional force, which is 3.92 times the distance of 5 meters times 5. Well, that gives us a value of 19.6 joules. Okay, so now we need to think. We have this ball, it's moving along with kinetic energy of 500 joules. And there is friction involved. So therefore, this energy is being transferred and the kinetic energy is reducing. So where is this energy going? It's going to thermal energy stores, to the ground, friction by friction, and air resistance. So we can find the difference of this energy here. So kinetic energy, which is 500, take away the work done, is how much energy this ball is going to have remaining. So this will be the change in energy. So plugging in the values, 500 take away 19.6 gives us a value of 480.4 joules. Okay, so now we know how much energy this ball has at the end, so we can plug it into our kinetic energy equation, which is half mv squared. And we can rearrange this for v as if asking for the velocity. So we know kinetic energy equals half mv squared. Rearranging this for v, which is equal to 2 times kinetic energy divided by the mass, square rooted. Now we can plug in our values. So 2 times, the kinetic energy is now 480.4 divided by the mass, which is just 1. So calculating this would give us value. Velocity equals 31 meters per second. Now pause the video here and attempt this exam question. A roller coaster has a mass of 1 ton. Calculate the kinetic energy of the roller coaster when it reaches point A and point B. So we know the mass, 1 ton, is equal to 1,000 kilograms. And to calculate the kinetic energy, we will assume the energy at the top is all gravitational. So we can work out how much that is. Gravitational potential energy equals mass, which is 1,000, times gravity, 9.8, times the height, which is 10. Okay, so that would give us a value of 98,000 joules. So at the top, This trolley or roller coaster has 98 kilojoules of energy in the form of gravitational potential energy. Now, as this roller coaster is going down, it is decreasing in the height, so therefore the gravitational energy is decreasing, and we'll assume that no friction is involved. Therefore, all the energy is moving into the